All right, we are going to start. Thank you.
All right, welcome to session 2. First, we'll be having Rachel Fowler, and her talk will be on how do climate factors influence shifts in dissolved organic carbon at depth and light attenuation in lakes in West Greenland.
Thank you. So I'm looking at how climate factors affect lake properties in West Greenland. And so you may not know that lake temperatures globally are rising faster than both ocean temperatures and surface air temperatures. So in the Arctic, where there's been recent rapid warming, these Arctic lakes are especially vulnerable to abrupt climate change. So the Arctic and the subarctic regions contain about a quarter of the world's lakes. And in this area of West Greenland, the Kangerlussuaq landscape, there are around 20,000 lakes dotting the landscape. And these lakes are sites of intense carbon cycling. They play really important roles in regulating carbon CO2 emissions to the atmosphere, and they also bury a lot of carbon in their sediments. So the question I'm asking is, how do climate factors influence ecological processes and carbon cycling in these lakes? So lakes exhibit really strong responses to changes in climate. So the coherence of lake responses, and coherence can be defined as shared variance in a time series. So the coherence of lake responses can tell us a little bit about what's going on with climate and how it's impacting ecological processes and carbon cycling. So the way this works is there can be some sort of large-scale, widespread climate factor that's exerting this, you can think of it like a footprint over the landscape, over this wide spatial area. And that creates coherent responses in lakes. And then in regions, smaller regions within that large footprint, things like different weather patterns can work to switch up the amount of coherence. And this is on the scale of tens to hundreds of kilometers. So in this figure, which is quite small, but we've got E and M inputs, and those stand for energy and mass inputs to catchments and lakes. So E can be things like solar radiation, heat, and wind, and mass is precipitation, particles, and atmospheric solutes. And these can work together to increase or reduce lake coherence. So the objectives of this study are to assess how coherent some DOC, dissolved organic carbon, variables are, and also light attenuation in lakes across several study lakes in this region. In 2 small regions individually within those regions, and then between those regions, looking at the coherence of some variables. And then pairing these lake data with meteorological data to get a better understanding of how weather patterns may be affecting some recent changes in lake responses that we've been seeing. So here's our study site in Southwest Greenland. This is the Kangerlussuaq region. These are the 2 main sites that I'll be talking about today, Kellyville in red and the ice sheet in black. They're situated across this climate gradient. And so Kellyville is warmer and drier, and the ice sheet is colder and receives a lot more precipitation. So in June of each year, from 2013 to 2017, we sampled a suite of lakes across these 2 regions. And today I'll be showing you data from 5 lakes in both regions. So these are the lake variables that we looked at: DOC, A380, and 1% PAR. So DOC, dissolved organic carbon, is organic matter that can pass through a filter, say a GFF filter. It can be autochthonous or allochthonous in origin, and it's ecologically extremely important because it has direct and indirect inputs to the carbon cycle. It also absorbs solar radiation, and it's an important food source for microbes in the lake. And then we have A380, which is an indicator of the type of DOC in the lake. So think terrestrial DOC. And this is the UV absorbance of water at the wavelength 380 nanometers. It also plays an important part in controlling the depth of 1% PAR in this suite of lakes. So that brings us to 1% PAR. It's the 1% attenuation depth of photosynthetically active radiation. So basically, water transparency. If you have a deeper PAR, you have greater water transparency. So with a higher A380 value, you have a lower PAR. They're very closely connected. And PAR is important for controlling lake thermal structure in this area. So in the figure on the right, I've plotted out some recent percent changes in these three variables in Kellyville region in red and ice sheet in black. So the y-axis represents percent change from the previous year. So this is one way of looking at coherence. And here's another way of looking at coherence. Because the lake variable values were so different in Kellyville and the ice sheet, I standardized them by doing a Z transformation. So on the y-axis, we've got the Z-score of each of the 10 lakes in this study. So you can kind of just do a very quick visual of how coherent they are over time for these three variables. So to quantify the mean coherence of each of these three variables within and between the two regions, we did Spearman correlations. So mean coherence is represented here by Spearman's rho on the y-axis. And there are two things I want you to take away from this figure. The first is that PAR, 1% PAR, is extremely coherent both within both the regions and between the two regions. The second thing I want you to take away is that in the Kellyville lakes, DOC and A380 have very high mean coherence, while within the ice sheet region and between the two regions, coherence is much lower. So one reason for that high coherence in the Kellyville lakes might be that they have a really high climate exposure index, or CEI. And the CEI is a ratio of a lake's surface area to its mean depth. So you can think about how with a higher CEI comes a greater exposure to climate factors. And if you have a lot of lakes that have a high CEI in an area like Kellyville, it makes a lot of sense that they would be exhibiting this coherent response. So the Kellyville lakes are represented on the end of this figure with the red kind of square drawn around them. So PAR exhibited the strongest within lake or within region and between region coherence overall. However, in 2015, that coherence kind of deteriorated between the two regions, which I've denoted with this yellow ellipse. So in 2015, PAR increased in Kellyville and decreased in the ice sheet. So using some data from the DMI, the Danish Meteorological Institute, and the GRASP project, we were able to have some data for, some weather data for the Kellyville region and also the ice sheet region. So meteorological variables like seasonal and annual precipitation, temperature, wind speed, air pressure, things like that. And what we found was that in just doing a preliminary look at the data, was that in 2015, Kellyville received less than 60% less precipitation than the long-term average, and that in the ice sheet, the average spring air temperature was 3 degrees lower than the long-term mean. So this got us thinking about the sorts of weather variables that could have an impact on lake properties. So we did a multivariate analysis called principal components analysis, or PCA, We did one for the lake variables and one for the weather variables. And we correlated the first and second principal components for each. And what we found was that DOC was strongly impacted by temperature variables, while A380 and PAR were strongly affected by precipitation variables. So if you take a look at this scores plot, what I want to show here is that the two regions aren't clustering apart from each other. They're pretty well integrated. And then on the loadings plot, you can see how DOC is high up on that temperature axis, and A380 and PAR are at opposite ends of the precipitation axis. So in conclusion, the main points that I'd like you to take away from this talk are that 1% PAR had the greatest between and within region coherence. So that indicates that there's this large-scale climatic footprint that's acting on the region and that's responsible for that coherence in PAR. Next, DOC and A380 were highly coherent in Kellyville, but not in the ice sheet lakes. This could be because Kellyville lakes had this really high climate exposure index, so they were all acting coherently together, where we didn't see that in the ice sheet. Also in the ice sheet region, there could be a lot of differing catchment and lake properties that kind of filter out that climate signal and play with the coherence a little bit, reducing coherence. And then finally, DOC was influenced mostly by temperature variables, while A380 and 1% PAR were influenced mostly by precipitation. And this could be to do with different sources of inputs to the lake. So for example, A380 is thought to be an indicator of terrestrial sources. So when we've got greater precipitation, we may have more A380 signal in the lake. And DOC can be produced within a lake by algae and macroinvertebrates. So with warmer temperatures, we may have higher net primary production and faster microbial breakdown of organic matter, resulting in more DOC. So thank you everyone who has helped with sampling and statistical advice and data sharing, and also to funding sources. I'll take questions. I don't know if I have time. Okay, thank you.
Okay, next we have Benjamin Seliger, North American trees, Underfill, climatic ranges.
Hello, everybody. Thank you for coming to my talk. My name is Benjamin Seliger. I'm a PhD candidate with Jack Gill, and today I'm going to be talking to you about some of my PhD work, where I've tested a major assumption of tools we use to forecast species ranges. And so that assumption is that species are in equilibrium with their climate. And what we mean by that is a species, if it's in equilibrium with climate, should be found in all the spaces which are climatically suitable for the species. So here you see the saguaro off in Alaska. It is not in climatic equilibrium. Climatic disequilibrium are when species lag behind climatic change. So the climate change, the pace of climate change exceeds the rate at which the species can respond to the climate change. And this is critically important for our ability to forecast species ranges, because as you imagine, if species are in equilibrium with climate, then they're just going to go where the climate goes. And our job of predicting where species are going to go is really easy. Wherever the climate goes, the species will follow. But if species are in disequilibrium with climate, then that means that we're going to have to consider many other factors, which I'll get to later, in order to predict where species will go, on top of the climatic change, which is already difficult to forecast. So to give you a visual of how we measure climatic disequilibrium, here we use this approach called range filling. So imagine a species range at the last glacial maximum. As the ice sheet melted away and the climate warmed, it would open up a large amount of potential range, which the species could then colonize. And we can estimate this potential range using distribution models. And so the amount of this potential range that you see here that the species fills is what we call range filling. And we use this as a proxy for how well basically how in equilibrium the species is with climate. And so various things that might keep a species in disequilibrium with climate include dispersal. So perhaps the rate of climate change exceeded the rate that the species could disperse. And so it has yet to get to these areas. And that's the main reason or the main mechanism we're most interested in, because that would suggest that species cannot keep up with climate change. But species could also be missing out of this part of their range due to competition with other species, or perhaps there are species with really particular soil preferences or something like that that could keep them out. And I'll come back to that later. So to give you an example of what this looks like when I run it on a real species, I'm going to start with the species range here, honey locust. And so honey locust is a tree that is not native to Maine, although we sometimes have it planted here. And you can see its realized range here. This is all the places where it's growing and reproducing naturally. So then I look at the climate within the species range and climate variables that I think are important for predicting where the species will be. And we've used these 4 climate variables to predict species or the ranges of trees. And these are growing degree days, which is a proxy of how warm the growing season is. Winter minimum temperature, obviously how cold the temperatures you have to deal with in the winter. Water balance, well, that's the amount of water that comes once you factor in for evapotranspiration. And then precipitation timing. So this is when your precipitation comes. You see the blue-green areas on the west coast, they get their precipitation in the winter. Areas like Florida and Mexico get their precipitation in the summer. For most places, we generally get relatively even amounts of precipitation timing. So going back to honey locust, when I've ran this model for the species, this is what I've found. And so all the areas above purple, the blue and yellow areas are potential range, with yellow meaning higher suitability of potential range. And this black crosshatch is the realized range where the species was found. So then I look at the percentage of potential range which the species actually is colonized in, the species realizes. And for this species, it is 69.9%, or about 70%. So that means that out of all the total values across this entire range, honey locust is only realizing about 70% of the potential area it could live in. And we also, if you want to talk to me later, but we downweight some of these areas which are blue. If we add up the values, meaning that areas that are blue are not as prioritized as areas that are yellow, which are higher suitable areas for the species to live. So I don't just do this for honey locust. I've done it for 477 species of trees, and this is just an example of what a suite of species ranges looks like. So we have honey locust there, but we also have some big ones like white spruce, but also very tiny ranges like this Carolina hemlock, and that's going to become important later. So I've run it through all these species and look at range filling. I've found this one main general pattern where the size of a species' realized range, as it increases, so does the species' range filling. In other words, large range species fill up their range very highly, whereas small range species are not filling up their climatic potential range. On average, you can see here it's about 25%. So a small range species means it's only filling up about 25% of its potential range that it could live in. And so this is very interesting, but it brings up more questions than it does answers. Why do these species not fill up this potential area? And there's many different reasons why that could be. This could be because of dispersal, as we talked about earlier, but it could also be due to competition. And so we want to be able to disentangle this a little bit to see if dispersal is driving underfilling of ranges. And so the way that we're going to do that is look at the shapes of ranges. So here on the x-axis, I have a longitudinal extent and just kind of an abstract space, and latitudinal extent on the y-axis. You imagine a species, a newly evolved species, growing and expanding its range. You're going to expect that it's going to grow isometrically in all directions, so long as it doesn't hit any area in which it can't live. Because right now it's expanding without running into any barriers. And we call this an intrinsic dispersal limitation, such that the species range is limited by its own ability to disperse and get to places. You can contrast that with climatic restriction. So here in the intrinsic dispersal limitation, you end up with a circular range because the species isn't running into anything. It's only limited by its own ability to disperse from its center. Well, here in a climatic restriction, you'd expect that you end up with a species range which is less tall than it is wide, because climate zones generally lie along east-west, along latitudinal bands. And so you end up with a squashed range, small in height, but wide. Conversely, if you're stuck in the mountains, you can end up with the opposite example, in which you have a very skinny but tall range. And so by looking at the shapes of a range, relative to the x-axis, the longitudinal axis, and the latitudinal axis, we can make some inferences about what limits the species ranges. I'll give you some real-world examples of what these look like. Here's one of a fir off in the Pacific Northwest. You can see with a very skinny but tall range. This one's probably being limited by getting over these mountains. You can see one down here, longleaf pine, that's growing in Florida, in which its range is fairly well matching that of what you might assume is its climate. It's matching along these latitudinal bands that you see up here from the USDA. And then lastly, this one down here, this horse chestnut, is probably an example of an intrinsically limited, intrinsic dispersal limited species in that its range is quite circular. It's not hitting any mountains. It's not hitting any ocean. It's probably being limited by its own ability to get places. And so you may remember going back to my general finding that species have higher range filling with larger sizes. We are interested in how these range shapes will correlate with range size. We might expect that if the small range species that had low filling before are being limited by their dispersal ability, then small range species are going to have more extrinsic barriers and more intrinsic dispersal limitation and less climatic restriction because they're not filling up their climatic ranges. And indeed, that's what we found. So I've displayed this in two different ways here. The same graph that I was showing you before in abstract space is now plotted out with real species, their real ranges in green and their potential climatic ranges in blue. So you can see what I told you before, that the climatic ranges should be more squashed and wide is true. You see the climatic ranges over the potentially climatic ranges over here, whereas you see the smaller range species lying along this 1-1 line and actually going above the line, like we might expect if they're limited by dispersal limitation factors. I've plotted this another way. Here, if you fell on this 1-1 line, you're now on this 1-1 line. And if you fall above the line, you are up here and below here. And I've plotted it once again against realized range size. So what you see here is that as your range increases in size, you generally move more towards a squashed, wider, but less tall range. And as smaller ranges, they generally tend to be more circular ranges, suggesting that they're not as climatically limited. So to summarize, the underfilling of potential ranges suggests that many species are not always where we would think they'd be if they're determined only by climate. And this is really important when we want to predict where species are going to go in the future. Furthermore, I found this interaction between range size and the range filling, suggesting that the small range species are doing even worse than what we thought, and that they're probably being limited by dispersal as the range shape analysis shows. And this is really important since most species that we're interested in the future in terms of conservation are oftentimes small range species. And so oftentimes people are forecasting small range species, assuming that they might stay in equilibrium with climate while not including their dispersal and how well they might be able to get to these ranges. So with that, I'll take any questions. Yeah.
How confident are you that the polygons from USGS are accurately depicting the species range?
Yeah, that's a good question. So what he's asking is, if I go back to these maps, there we go. How confident am I at these ranges actually showing the true range of the species, correct? And that's awfully a good question. It's pretty difficult to necessarily assert where the species is growing naturally versus where it might be introduced sometimes, like honey locust. The person that did this was the chief dendrologist who spent many years talking to people where they're growing and reproducing naturally versus where they're just introduced by people. And so we do know, for instance, honey locust, it's growing here in Maine. However, we'd have to see if it's reproducing and competing with the natural suite of species. Yeah.
Are the species that have a more restricted range, are they ones that have dispersal mechanisms that would not allow a more distant dispersal?
Yeah, that's a good question. So what he's asking are small range species, ones that would have dispersal strategies which would appear more limited. For instance, if you had a larger seed, you're not going to be able to disperse as far. So that's been a major question of several of my chapters. And the long and short of it is generally no, that we don't find that the dispersal adaptations match on with the dispersal limitations like we might expect. And basically the short explanation of that is dispersal is really random, we think, in that the dispersal that's driving these long distance range shifts tend to be chance events, which oftentimes don't incorporate the mechanisms which the species is adapted for. So you might imagine a tornado can come through and throw a seed a very long distance. And that seed might grow on to expand the range much more so than dispersal happening on a more local scale. So basically these chance events, which are really rare and the species are not adapted for, are really important. Yeah.
I'd like to turn around the question from earlier about the validity or accuracy of these range maps.
Mm-hmm.
That's a good question.
Yep.
My question is, how confident are you in the climate version of those maps? And the reason I ask is because we know many species can be planted outside their ranges and do perfectly well. They're given a head start, they can grow through their life cycle, but
right.
almost never reproduce. And that's true of most of these things. So they're planted, unless the climate has changed enough for them to be in a climate zone that's equivalent to what they were before. So, because quite often, the life cycle phase, such as the seedling phase cannot be completed for one reason or another, whether it's being eaten by something or pests or something, or just can't complete because of climate reasons itself. So even though it might appear that it's climatically suitable, it actually, in fact, isn't in terms of a sustained population.
That could definitely be. These climate variables are an average from 1970 to 1990. And I'm sure many of the climatologists here would like to tell me about their limitations or various ways that they could be improved upon. These are generally a standard we use in species distribution modeling. However, like you said, they're probably not capturing any sort of interannual variability. They should, fortunately, match up their 1970 to 1990 average, and that should relatively match up to when the person was making these maps. He was drawing them in the late 70s into the 80s. So hopefully we shouldn't be getting too much temporal mismatching due to climate change driving species distributions. Hopefully that should be taken care of. Yeah, and I'd be happy to talk later. I think I'm out of time though. Thank you all.
All right, next we have Elena Korotkikh, developing an ultra-high resolution record of the Termination 2 in the last interglacial from the Allan Hills Blue Ice Area in Antarctica.
Hello everybody, my name is Elena, I'm a part of Ice Core group, and today I'm going to show you some preliminary results from our Allan Hill Blue Ice Area project. It's still work in progress. I was just analyzing some ice section last week, but we already have very interesting results and I'm very excited to show it to you. So in my talk I will describe, give you a little bit information about Allan Hill Blue Ice Area site and previous work. Then talk a little bit about our laser ablation ICP-MES facility and show you some results with annual signal, volcanic signal, and changes between glacial and interglacial conditions. Allan Hill Blue Ice Area site located on the edge of East Antarctica sheet, and it's a unique site because the oldest ice on Earth have been found here. The ice, the meteorite ages suggest that the ice is old as 2.2 million years old. And this site is also unique because it has very good records of the last interglacial, the Eemian or marine isotope stage 5. Previous work, Nicole Spalding and Andrei Kurbatov, they collected some surface samples and drilled they collected vertical ice core, and it shows the surface sample shows here, the Deuterium records from vertical ice core shows here. So as you can see, it covers the Eemian interglacial termination 2 in the previous glacial period. So we decided to sample some of this ice using our laser ablation system. You probably heard already about the system, but I will give you a little bit more information. So the system, we have an ice chamber, which we cool down and we put ice inside. We can fit 1 meter of the ice core. And then the laser, it's ablated the ice material from the surface, and you can see the ablated path on the screen. The ablated materials are carried away by argon gas to the ice pyramids. And we can measure several elements. We focus on sodium, iron, aluminum, magnesium, copper, and lead. The advantage of the system, because we can create extremely high resolution records. Like normally, if we analyze ice core, we use a continuous melting system, and we can get about 100 samples per meter. With a laser system, we can get 20,000 samples per meter, which is much more high resolution. And it's especially great if you want to study some old, very compressed ice. So we analyze few sections of the Allan Hill Blue Ice Area ice. So far, we analyzed 3 meters. And as you can see, we got really great results. This section covers the ice from 138.4 thousand years ago, from the glacial period, and it's only like a few centimeters. So in this very old compressed ice, we can see annual layers. We can see the increase, like variation in the iron, aluminum, and magnesium, which we believe those elements represent dust signal. And you can count individual layers here. And our layer counting corresponds very well with the depth age model developed by Nikki and Anthony. And I just plotted here, like remind you, if we use continuous melting system, which was like traditional ice core sampling, for this section, we'll be able to get only 3 samples. And using laser system, from this section, we have 600 data points. So even a few years ago, we will never be able to see annual layers in this deep compressed ice. And now we have this beautiful record. And if I just zoom in 2 years, like the sample resolution is amazing. It's only like 0.7 centimeters per year, the annual thickness here, and we can get 35 data points per year. So we could not just count individual years, we can also compare like how different years, like to see similarities and differences between individual years. Because they're not the same. Some years you have more dust, some years you have less dust, and we can see like seasonal signal also. So this plot shows the all laser data we have so far. We sample few sections, like this 3 sections during the glacial time. You can see by the isotope low values. And 1 small section during the last interglacial. And this is 3 dust elements and sodium, which is mostly come from marine aerosols. And not surprisingly, we see during the glacial time, when it was cold, we see much high intensities of the dust and sodium. And during interglacial time, we see decrease in dust and sodium. And you can also see on this table, it's really like clear relationship. When it's like warming up, we see decrease in aluminum, ferro, magnesium, and sodium. And that's what we expected to see, but we also decided to compare with Taylor Dome record, which is located very close to Allan Hill. This plot on the top shows deuterium record, red from Allan Hill, and green, it's a deuterium record from Taylor Dome. And on the bottom, our laser data, magnesium, and brown, it's a magnesium from Taylor Dome. And as you can see, from 9,000 years, Taylor Dome has only like 8 samples. And we did not analyze the whole record, we just analyzed like a few sections, and we already have like about 45,000 samples. And they show the same pattern. We see more magnesium during glacial time and less magnesium, less dust during the warm interglacial conditions. If I, like the most interesting kind of feature on this record, we see this huge decrease around 138.5 thousand years ago. If I zoom in, we can see a lot of variability in the signal. And again, I plot the isotope records. So you see when it's cold, we have more dust and more marine aerosols. It starts warming up, we see decrease in dust and marine aerosols. And again, with this laser system, we can see how fast these changes happened. Like you see this big transition, decrease in dust and marine aerosols happened in less than 100 years. And some of the transition was even happening like during the 10 years. So it was like before we would never be able to capture these little variations. Because we have these three elements which we believe comes from dust mostly, we want to see the ratio between them to see if this dust source remained the same during glacial and interglacial conditions. As you can see on this plot, they look quite different. During interglacial, the samples are more compact, so it shows probably limited dust source. And during glacial conditions, they more like they covered a larger area, which probably represents that dust from broader sources were coming from Allan Hill. And this is consistent with the previous model studies, which shows like during the present time, for Allan Hills, dust was mostly coming from Australia, and during glacial conditions, a lot of dust from South America were reaching Allan Hill Lewis areas. Another very interesting record we saw this huge increase in copper and lead. And it's not related to dust because, as you can see, dust remains quite the same. And copper and lead could come from volcanic emission. So we thought it could be volcanic signal. And not surprisingly, exactly pretty much the same age. It's been a volcanic eruption from Mount Berlin. And the tephra from Mount Berlin had been found in Mount Molten area. It's right next to Mount Berlin. And it's been dated. So, and our dating of the tephra matched our dating pretty well. And this tephra has been found in everywhere in West Antarctica, in Vostok, and Epicodome Sea. So we kind of expect to see it in the Allan Hill site also. And if you zoom in, just this yellow square, we could see this volcanic event in great detail. So we could not just tell, yeah, it was like one volcanic peak. We can see how many years it lasted. And it looks like it was at least two big events. One was lasted maybe 3 years, another one 2 years. So just to summarize, our preliminary result shows that laser system could give us extremely high resolution record of the very old compact ice. Like for the first time, we'll be able to see sub-annual record from the glacial ice from stage 6 and from last interglacial. And we're going to continue to sample more of the Allan Hill ice, and we're going to try to sample also very old 2 million years old ice, and hopefully soon we'll get more interesting results. Thank you. Thank you.
Okay, great. Next we have Emily Blackwood, seasonal analysis of 3 middle woodland archaeological sites in eastern Maine using modern and excavated marine bivalve mollusks. I'm not going to try this.
Steamers. Yeah.
All right, so I'm Emily Blackwood. I'm a third-year student in the Quaternary Climate Studies program with focus in archaeology. Switching gears a little bit here, talk a little bit about some shells and some archaeology in the context of them. So along the coast of Maine, there's roughly 2,000 archaeological shell middens. What a shell midden is a refuse pile where discarded materials such as bone or broken stone tools or such are left behind by Maine's native peoples. David Sanger has developed a theory where there's two populations of Maine's native people, an inland population and a coastal year-round population. So what I've been doing for the past few years is looking at whether or not we can find any validity in this using modern and excavated shells, which is something that hasn't been done before. So my research question is, can oxygen isotopes from modern and excavated shells be used to establish a season of occupation at 3 shell midden sites along the coast of Maine? These shell midden sites are Holmes Point East and Holmes Point West, as well as Jones Cove. And to address the seasonality question, or when these sites were occupied, we're using the oxygen isotopes within these shells. So Jones Cove was originally excavated in 1928 by Dr. Warren Moorhead. They used clam rakes, and there was no screening that took place. Not great procedures as we know now. It was revisited in 2006 by Brian Robinson and the Maine Field School, and it was quickly found to be very disturbed, where you can see outlined in here in red, it's all the disturbed, and then these little blue areas are undisturbed. So really the only way to address what the context of this site and what it was used is to do a seasonality test. However, shell was not collected during the excavation, so I had to go to the column sample, which was taken here, and that is where I obtained my archaeological shells for this study. It's been dated to a middle woodland site, and it's been hypothesized to be a winter occupation based off of faunal assemblage and tomcod, which only spawn in the winter. Now going to Holmes Point East and Holmes Point West, these are located in Machiasport. They've also been dated to a middle woodland site and up and through contact period. These sites are a little bit different in that they are hypothesized to be a summer occupation site, and this stems from the assumed association of a very large bedrock outcrop located directly across the bay, where there's a large series of petroglyph images that are pecked into the stone, the bedrock. This is an example of one of those here. They represent anthropomorphic figures, animals, and the final two are images of a clipper ship and a cross. Down here, we have an example of a wall profile from Holmes Point West. The solid blue line and the dashed blue lines are representative of where the shell is within the site, and the dashed blue line is located over one of the features within this site, which is one of the units that I chose to use in this study, along with 3 others that are corresponding to a seaming feature, the largest concentration of chamber pod in the site, and a unit from the back perimeter of the site. Holmes Point East, represented here, is 300 meters east of Holmes Point West, and they're thought to be contemporary sites. Holmes Point, they were both excavated in 1973 by Robert McKay, and then again from 2008 to 2014 with Brian and the UMaine Field School. And they are, again, hypothesized to be summer sites. So Jones Cove, we have a winter site. Holmes Point, we have summer sites. So the shells that are at these sites are Maya arenaria, soft shell clams, steamers. I'm sure most of you have probably eaten some of these. And they live in intertidal areas made up of mud, sand, and gravel. So over here, this is a live clam living in the mud, just hanging out before I took it out and ended its life. But all in the name of science, right? So within these shells, we can see their mineralization lines and their annual growth bands. So here, I've highlighted in red, this dark line here is winter growths. Because of where we are, the water gets very cold, and during that time, these shells don't grow a lot. The space in between is warm water growth. So between this dark line and this dark line is representative of 1 year's of growth. Clams are filter feeders, so they pick up the ions within the water, which make up the calcium carbonate of their shell matrix. And from these ions, what I'm using is the oxygen isotopes of O18 and O16. which fluctuate depending on the time of year, and the season that it is. So to do this type of collection, I spent from 2016 to 2017, I went to the clam flats near these sites every month and collected 10 to 15 samples of shells in order to understand what their isotopic signals were so that I could compare the archaeological samples to them. So here's some clams that were dug up, digging up process, archaeological samples here, and this is an image of what it looks like when we were excavating the site at Machias. And then here are all the samples that myself and Kate Pompran, who you will hear about tomorrow on a very similar topic, brought to Iowa State University to run using their mass spectrometer. While we were there, we're looking at the analyzing the ratio of 018 to 016, which, as I said, changes throughout the year. In order to do this, you have to mill the outer edges of the clam here and the chondrophore here, because the chondrophore and the outer edge of the clam, the outer edge of the chondrophore, will represent the same types of data. So you have a little bit of a cross-check between the types of analysis that you're doing. The chondrophore is a more condensed version of this, but it acts in the same way as a tree ring. So when there's rapid growth, you have small bands, larger bands. Slower growth, you have smaller, darker bands. Getting to the results. So at Jones Cove, over here on the graph, we have, we averaged the monthly modern samples of the isotopic signal from the shells and created error bars using the analytical uncertainty from the mass spec. And what these error bars do is you can create a range over here, which signifies where those what the isotopic signals from the modern shells are. And what you can do is then you make a table over here. So we have blue is the colder months and green are the warmer months. And as you have the ranges from the analytical uncertainty over here, you can then compare the archaeological samples up here to the known ranges of the modern samples and see where they fall in. So for Jones Cove, we have a pretty solid cold water signal that's suggestive of winter occupation, which falls in line with the hypothesis for this site. I would like to point out that there's a couple months here, February and March, where I was not able to collect data because the access point to the flat was iced over and I didn't want to fall. And in October, I was not allowed to collect because there was red tide and the wardens would not let me go out. Going to Holmes Point, I'm going to talk about Holmes Point West first. Again, we have the same as we did in Jones Cove. We average the monthly modern samples and you get the analytical uncertainty, which you can create the range. And what is important to note is that these ranges here are different than the ranges were in Jones Cove. So it's really important that you get data localized to where you're going at. So you compare the archaeological samples to the known ranges, and here we have a little bit of overlap, and that's because the ranges themselves overlap within themselves, but still, without including the overlapped ones, we have a very warm water signal suggestive of summer occupation, which again falls in line with the hypothesis. Going to Holmes Point East, we have a very similar situation with a little bit of overlap with the cooler months and the warmer months, but again, suggestive of a overall summer occupation. So some future work that needs to go into this. We have some more modern shells that we need to sample to go into the monthly averages to get a better idea of what's going on there, to make sure that we have an accurate representation for the ranges of what those averages are. I need to reassess the Holmes Point East and the Jones Cove collections because those came from column samples, and there are additional column samples where I can look to see if there's shell that's viable for this types of tests. And then once I do that, I can make final conclusions as to the season of occupation at these sites. I'd like to thank my committee and everyone who helped, especially Dom, who went out every month with me, no matter how early it was, and helped me collect these samples, as well as the funding, MAPI grant, and the graduate student government, who allowed me to have funding to run these samples. Thank you. If you'd like to talk to me about this further, I also have a poster out back, so anyone who's interested in clams, I'll be out there.
All right, great. So next we have Heather Clifford. The 2,000-year-long European Alps ice core reveals new climate proxies.
Hello, I'm Heather. I will be discussing new climate proxies from European Alps ice core. So the foundation of my research is based on the Initiative for the Science of Human Past, where CCI has partnered with Harvard historians to better understand interactions of humans and climate, how they're interlinked, and how humans respond to climate change. So it's important to study this, to study these relationships to help us understand how humans will respond to climate change in modern day and in the future. So the intervals known as the medieval warm period and the Little Ice Age are examples of climate change on a human scale. So famous artwork during the Little Ice Age, such as this painting from the 1600s depicting a frozen canal in the Netherlands, is an example of how humans have documented how they have responded to climate change in the past. So in 2013, CCI drilled and analyzed an ice core from Clifford glacier in the Swiss-Italian Alps region. And in the European Alps, the Clifford glacier stands out as the only non-temperate site where net snow accumulation is low enough to provide records that span at least the past 2 millennia. And so previous studies from the Clifford ice core record have revealed new information about this area. So for examples is, as Laura discussed, a lead record that spans the past 2 millennia that shows a significant decrease during the Black Death pandemic from Moore et al. Better understanding the relationship between temperature and mineral dust variability in the Clifford region from Oliver et al. And also a new multi-element method for laser ablation ICP-MS using ice cores. And so these studies have helped me, led to my research, which I have been analyzing and interpreting the Clifford ice core. So ice cores provide the most detailed, most direct and detailed evidence of past climates and atmospheric conditions. So we sampled 26 elements using the traditional discrete and depth-linkable plasma mass spectrometer, which Charles discussed earlier, and this is iron showing in red. However, at specific depths of the ice core, it's too highly compressed to get environmental details on, say, a meteorological scale. And so we also measured 7 elements using the laser ablation ICP-MS, which is non-destructive, which Charles and Elena have previously discussed. So in gray, we have the machine output of the laser ablation, and black smooth of iron as well. And so as you can see that they followed similar patterns. And so also for more information on the methods, I have a poster in back, which I can discuss later. So from the 26 elements that we analyzed using the ICP-MS, we need to separate these out into different groups by different corresponding groups by percent variance. So we applied a principal component analysis. And so we attribute these different PCAs to different air mass sources to the Clifford region. And so the first PCA with 57% of the variance, we attribute to Saharan dust due to the associated elements. And we also know that Sahara is the primary source of dust to the Clifford region. And PCA2 with 10% of the variance, we associate with rain due to the elements of sodium and potassium. PCA3 we associate with anthropogenic sources due to lead and arsenic. And also we can see at the end of this PCA an increase around the 1850s and a significant decrease in the 1970s, which we attribute to the lead abatement regulations. And then PCA4 with 6% variance is significant because the associated element is bismuth, and we know that this is associated with volcanic and anthropogenic inputs. And so looking at PCA1, which is 57% of the variance, so it's a significant air mass source to the Clifford region, we see a significant climate anomaly around the 900 to 1,000 interval, so we will look further into that. So looking further into this, this time interval, we can see that use PCA1 to Saharan dust proxy and also the ICPMS iron raw data, that you can only get about decadal resolution at this depth of the core. And so we're able to enhance our data by looking at the our laser ablation ICPMS record for iron. And so here, what we're seeing is in gray, this is the machine output from the laser ablation ICPMS, and in black is the annually resolved data. And so instead of just seeing 3 different peaks from the annually resolved data, we're seeing 9 and even further information if you're looking at the machine output. And so we also know that the 900 to 1,000 year period is the driest interval of the medieval warm period. And so this is now we're moving into how dust, how the climate causes these dust events. And so to further explore this, we calibrate our record of from the modern day to a climate reanalysis. So on the left here, I am showing our modern day dust record from 1870 to 2008. And in the blue, you have PCA1, the Saharan dust proxy, and iron, and also the Mediterranean June-July mean sea level pressure. So Clifford is a strong summer signal, so we decided to focus on the June, July, August summer season. And we correlated our Saharan dust proxy to sea level pressure, to known sea level pressures, or pressure systems in the northern hemisphere, and we determined that a increase in sea level pressure also corresponded with an increase in dust events. And so if you're looking at the highlighted area, which is 1984, which is a known Saharan dust event, you can, using the climate reanalyzer and the ARI interim climate analysis data, we can also see that this supports our hypothesis of the high sea level pressure in the Mediterranean along the North Atlantic. So another part of our, another objective of our research is comparing our records with historical records. And so the historians that we work with put a geodatabase online with historical evidence on health and climate. And so as you can see here, they've put together different epidemics, plagues, shortages, and by their strong, moderate, and they give us a record of, what's happening and throughout the Mediterranean. And so this is a very detailed record, and there are multiple meteorological scale events happening for each year that they document from the historical records. So to assist in the development of this unique historical-based ice core record, machine learning algorithms are being tested to look at environmental signals from the ultra-high resolution time series in concert with the historical records to compare the frequency of the meteorological scale events found in written records with the ice core dust proxy for a more comprehensive understanding of human and climate interactions. So in conclusion, we established proxies for Saharan dust, marine, anthropogenic, and volcanic air mass sources of Clifford. In addition to climatological events, our record captures meteorological and seasonal scale events, which is made possible by the laser ablation analysis, which I forgot to mention that we created the highest resolution ice core record yet with measuring close to 5 million data points for 40 meters of core, thanks to Elena, Sharon, and Nikki. And also, our Saharan dust proxy allows us to investigate the link with climate surrounding the Mediterranean over at least the past 2 millennia. And combining our knowledge of history and climate can bring to light the experience of past populations and help to explain the present by studying the past. Thank you.
All right, great. For the end of session 2, we have Julia Simonson evaluating numerical simulations of the December 2013 ice storm across Maine.
All right, good afternoon. I'm Julia Simonson. I'm a PhD candidate, and I work with John Merkel as part of the Maine State Climate Office. And so today I'll be showing you some of the results of my recent simulations of the December 2013 ice storm. So just to kind of give you a wider look at Maine's climate, we can see from past observation record that the statewide annual mean temperature and total precipitation have both increased over the past century. Now, what I'm specifically interested is kind of dissecting more of this precipitation aspect and looking at extreme weather events and how they have changed in the past and how they may change in the future. I'm specifically looking at the December 2013 ice storm. It's a much more recent example, but similar in its intensity and damage extent as the 1998 ice storm. However, being a much more recent example, there's a lot more data available and it's very useful for model validation. And so there's very sparse literature focusing on model-based examinations of ice storms, which is a bit of a shame because these are damaging storms and they can be very difficult in forecasting. Now, and in terms of modeling, this is difficult because processes that happen at subgrid scales are represented through parameterizations. And there's a wide variety of these types of parameterizations, and the specific choice is dependent on characteristics of the domain, such as topographical features, as well as kind of the average climate during that season, and then the very specific conditions of any one particular event. And so I've had to go and run many different simulations using different parameterizations as a way of seeing where the model does well and where it doesn't, and then which ones are closest to observed values. And so the model that I use is the Weather Research and Forecasting, or WRF model. This is a regional model, mesoscale model, and it is used as a dynamically downscaling method. So what you do is you take low resolution data such as reanalyses or GCM data, and you run it through the model, run it through the dynamical solver, and end up producing these lovely maps of higher temporally and spatially resolution variables. And what I'm particularly interested in the case of an ice storm are the parameterizations focused on modeling the planetary boundary layer, or the PBL. And these are the levels of the atmosphere that are directly influenced by the Earth's surface, so heating and cooling. And in the case of an ice storm, these processes are important because it directly affects the temperature profile in the layers closest to the atmosphere, and thus the type of precipitation that's going to reach the surface. So the simulations, these are 5-day simulations, giving about a day on either side of the event. And I am using 2 nested domains. So we have this 9-kilometer domain over the eastern United States and parts of eastern Canada. And these provide the boundary conditions then for the higher 3-kilometer resolution domain over New England. Now in the vertical, I've got 36 vertical levels, which in WRF are a pressure-based system. And these follow topographical features. And unlike what the diagram suggests, these levels are not evenly spaced, but they're much closer to one another, closer to the surface, and then higher up in the troposphere, these are much larger group spaces. And for my input data set, I'm using the ECMWF's interim reanalysis. So now let's look at some results. This is what's called a skew T log P diagram. So we have pressure as a coordinate here, and then temperature is skewed diagonally. And I'm comparing the model profile, which is red for the temperature and green for dew point, and comparing it to observed values of temperature and dew point, which are in blue and black. So for the upper tropospheric levels, the correlation between the model and the observations is very high. It's close to 1, and it's typically in the lowest layers where we get the largest deviations between the observations and the model. But even though the temperature inversions in general are well resolved, it is those the fewest layers that are near the bottom. So this is a plot of station temperature. So this is 2-meter temperature looking at Bangor International Airport. You can see that there is kind of a large spread between all of the different simulations compared to the observed values. It is very much time dependent, so dependent on the specific conditions at the time. However, there is this one really strange feature that I found at many of the locations. And it's particularly in the last 24 hours of the simulation, see this large cold bias amongst all of the simulations. And it turns out this is a result of a well-known model bias. And so during this last 24-hour period of the simulation, we see that the storm is moving offshore and the skies begin to clear. And it is during these types of conditions in which there is a lack of cloud cover that the model has a tendency of leading to excessive radiational cooling at the surface in locations that have snow cover. So in Bangor, there was a snowpack at this time, and so the model 2-meter temperatures are looking to be colder than what they actually were. And many of the studies have shown this in the literature, not just in terms of snow cover, but just generally in overnight hours, because they're very stable conditions. We have laminar flows, so more horizontal movement than vertical. And just at the subgrid scales, the model has difficult times handling this. And so just kind of in summary of the results I've shown you, that in general, WRF does quite a good job at modeling the temperature profile through much of the troposphere. However, it is those critical levels close to the surface where things start breaking down, which is very problematic and difficult being able to look at one specific event in history if the model isn't doing a very good job at it. And sadly, it's due to a known model bias that affects even forecasting models. And thus now I have to look into how I may be able to overcome this. And with that, I'll open up for questions.
Once your methods are refined, would you be able to go back and try to model something like the 1938 ice storm where we wouldn't have this really nice high-resolution instrumental or satellite data?
I'm not really sure necessarily how you would go about it, because it would be, I guess, possible, because there are ways in which people are able to simulate paleoclimate so conditions much far in the past, but it's very different in its approach versus using a reanalysis data set that gives the subdaily time scale of these types of variables. So I'm not really sure if I'd be able to come up with as nice of a simulation or as nice of results for that type of an event.
So, hi, I'd like to introduce our next speaker, our invited speaker. It's Dr. Rolf Mondell. He is a distinguished professor at the University of Kansas.